singular value decomposition based methods. Okay. You looking at some interesting lecture slides taught by two of my former collaborators and fellow mates in this research in model order reduction, Kenji Fujimoto from Kyoto University and Jacqueline Scherpan from the University of Groningen, my former PhD advisor. Okay. This is a class taught at the Dutch Institute for Systems and Control in Utrecht, in the Netherlands, sometime in 2017. And we're going to go quickly, do a recap and look on or check balance truncation from a different perspective. Okay, essentially this is a nonlinear perspective of things, but this is important to remember. Balance truncation is one of the, or as the most important model order reduction technique, okay, with sound theoretical results. And then, as you can see here, we have variations of the balance truncation where probably we have the closed loop balance truncation included, okay? All right, so what should be preserved? This is the main question in model order reduction. You do model order reduction, you do an approximation, okay, of some dynamical system with a lower dimensional dynamical system, and your question, you ask yourself, where or what are you going to preserve in this model order reduction procedure, okay? Which property has a priority and which is most difficult, okay? The idea is that you would like to minimize some sort of error where G is the original model and G hat is the reduced order model, and you want to preserve, and we have already discussed that, okay? We covered this subject last time. You need to minimize some approximation error. Probably will have infinity, usually you have infinity or the 2 norm of the error. These are the usual measures of error which need to be preserved. We need to preserve stability. We also need to preserve other properties such as controllability, for instance, or observability, or other structural procedures. And there is a lot of literature on different subjects of physical systems, such as port Hamiltonian systems, mechanical, physical systems, and so on and so forth. Okay. They say here, it's very interesting. Historically, the priority was in the beginning, the priority is 1, 2, and 3. So you want to minimize an approximation error, you want to preserve stability, and then you want to preserve structure, okay? And the difficulty, they claim here, is in the same order. This is more or less true because essentially the problem of minimizing the approximation error of in model order reduction, so this problem, min by all transfer functions G from G minus G hat, some sort of norm here, doesn't matter which one. This is a non-convex, non-linear, and infinite dimensional optimization problem. Okay, so it has all the bad ingredients, I'm afraid. So I don't know why they claim here, well, that's the view of things, that's their view of things, that these are more difficult. Because stability preservation, I'd say, is not so difficult. Or, oh, no, I think they are right. No, I'm sorry. No. If you look at this trait, 1 is the most difficult, indeed. Okay, now it's correct. This is correct. 1 is the most difficult. No, now I read it correctly. This is the most difficult. And this is the easiest. Sort of. Let me put it like this, in quotes. Okay. No, it's correct. Sorry, I misread it. I misread this. This is correct. 1 is the most difficult. That's my view, and that's what I was trying to tell you here. Why is 1 the most difficult? Okay, 1 is the most difficult. 1 most difficult. 1 is the most difficult because it's a non-convex, non-linear, and infinite dimensional optimization problem. Okay. And since you probably have all attended some sort of optimization class, you understand what this means. Okay. Recently, there is a lot of attention paid to 3. That was in 2017. This is also today in the context of complex systems, interconnected systems. I mean, graphs and networks of systems, which are very difficult. Okay. Hence, the preservation of some sort of network or graph topology of some huge dynamical system made of smaller dynamical system of several components. This is really important. Okay. Oh, okay. I got some important message here. Thanks. Right. Okay. Yeah. Usually, as we have seen, projection-based model detection methods are easily modified to cope with structure preservation objectives. Okay, easily modified. This is also this is a bit adventurous. This is not so easy, if you ask me. But indeed, they can be there are projection methods which help us preserve specific topologies. Okay. All right. There are some examples presented here, which I think that's why I think these slides are very useful to you if you want to grasp the meaning of model order reduction based on balance truncation. A typical procedure of projection, they say here, based reduction is the following. You apply an appropriate coordinate transformation and you make the new state to be x1 and x2. This is what balance truncation does, such that x1 is more important than x2. That's true. And we already know that, but they're going to remind us. See balance truncation. Okay. See the balance truncation, because this is what happens in balance truncation. Then you apply a projection. You say that x2 is phi of x1 and u, and the remaining of dynamics x1 defines a reduced order model. This is what balance truncation does, if you remember. Okay. You only select that part of the dynamics gathered in x1, which is more relevant if you compare the Hankel singular values associated to x1 with the Hankel singular values associated to the x2 part. Okay? And then you truncate x2, or you do singular perturbation, and you get your reduced order dynamics. In POD, proper orthogonal decomposition, we haven't discussed it here, but it's pretty much the same. That looks at snapshots of the state and gathers them in all sorts of matrices. Then you build a projection based on these matrices of snapshots of the state. Okay, and this shows you how you make the model reduction, how you perform the truncation. Okay, this is x1 and x2 dot. This is the dynamics split into blocks accordingly. And then you do the projection means that you take x2 equal to 0. Okay, and then the reduced order model is this one. Okay, this is the way model reduction has been done so far in balance truncation, Hankel norm approximation, and essentially all the SVD-based techniques. Okay, you can also do singular perturbation in the sense that you take x2 dot equal to 0. We've done that before. And then you pick x2, and this is the phi that you can define in the first algorithm. You take x2 to depend on x1, and then you put it back in the equation of x1. And then you get the reduced order model with a singular perturbation type in this fashion. Note that this time you can also get a feed-through term in the reduced order model if you do singular perturbations. Okay. Why? Because x2 depends explicitly on the input term. So when you do singular perturbations, essentially you get in the output, even if you didn't have it before, you get it because of this term, because you cannot make it 0. You get this direct influence of the input over the output. This is in some way it's a drawback, because essentially your original system might not have, which is the usual case in engineering. The original system does not have a feed-through term, does not have a D term, but you do model reduction and you end up and some strange D term pops up from nowhere, out of the blue, and that's not pretty much desired. So that's why in general people do not spend too much time and do not necessarily perform singular perturbation when they do. They just do truncation and that's it. Another method we haven't discussed very deeply so far, but which is quite important, is a mechanical system of this form, for instance, where you can do a mode decomposition. Okay, mode means that you look at the eigenvalues of some matrix and you split the state into blocks according to the to the um, to the magnitude of the eigenvalues. You do the projection in this form, and then you get your reduced order model of this form. Note that if you do this kind of truncation, of model truncation, the structure of the mechanical system is preserved. This is again a mechanical system, which has a mechanical system that has uh, here. This is the acceleration term, and this is the potential term, and so on and so forth. Okay. Okay. Key ideas of balanced truncation, they say here. So you must have structure preservation. So you employ a specific type of projection. Okay. Because you select particular energy functions, and we already know we have the controllability and the observability functions. Okay, there's two of them in balanced truncation, of course. You do stability preservation because the Lyapunov functions are essential. That's why, actually, that's why the balanced truncation preserves the stability, because it preserves the energy functions, and one of them can be used as a Lyapunov function to determine the stability of the system. Okay, that's the funny thing of it. Okay, when you have the observability Gramian, all right. So yeah, that's a Lyapunov way of thinking. Okay, so you have x dot is ax and y is cx. This is for observability. Okay, and you take the LOX, okay, which is the controllability energy function, okay, which is the integral from 0 to infinity from y squared t dt. This can be called Vx. This is like it's positive definite, okay, for all x non-zero, and LO of 0 is 0. So this is what they call in nonlinear system a Lyapunov function. This is a Lyapunov function, Vx. And if you do, and it's usually given, this is half x transposed, observability Gramian. This is the observability Gramian. Okay, x. All right. And how do you assess stability in Lyapunov way of thinking? You look at the evolution of the energy along the trajectories. Then you do v dot x. Okay, this is the time variation of the energy with respect to the trajectories of the system. And this is what? This is what? This is x transpose dot mx, you agree? Plus x transposed mx dot. This is the way you apply the differentiation. You agree? Because x depends on t and m is constant. Okay? This is how you perform differentiation. But you know that x dot is ax. That's what we have here. Then you substitute it here. So this is further X transposed. X transposed. I think we should also have a half here. Never mind. X transposed. No, X dot transpose is X transposed A transposed M X plus X transposed M A X. So you can write this as half. This is half X transposed A transpose M plus M A X. But we already know M is the observability Gramian, so A transpose, okay? A transpose M plus MA plus C transpose C equals 0. So this is minus half C X transposed C transpose C X. This is like this, okay? And A is already stable, we already know that, okay? But this is related to stability, okay? But when you perform model order reduction, you end up in balanced truncation with A11 transposed, of course, tilde, sigma plus sigma A11, okay, tilde, plus C tilde transpose C equal to 0. This is of the reduced order model. And it's the same, of the same type. It's of the same type. So indeed, the Lyapunov functions are preserved. Okay, that's why stability is preserved in balanced truncation. Okay, that's why stability is preserved. Okay. Minimizing the approximation error. No, we just get with balanced truncation we get an error bound. That's all we have. Okay, in balanced truncation. Okay. Okay, how to approximate linear maps with a low rank approximation. Okay. Approximation A is is defined on X taking value in X, whose rank is rank A is K smaller than N. How do you get A hat? Okay, for a linear map, A psi is lambda psi. Okay, this is the eigenvalue. This is the definition and of the eigenvector and the eigenvalue of a linear map. If you diagonalize, okay, you get A psi1 up to psi n equals A psi1 up to psi n. This is the diagonalization transformation, okay, times the diagonal matrix of the eigenvalues. We know we can do that. This is the usual way to perform diagonalization. Okay. Then A is of this form. This is the original matrix. And then you approximate by truncating, taking only this part of the original matrix. Okay. And using the same transformation T. Okay. When you do this, can you compute the error bounds of then some norm of A minus A hat? Okay. When A general A and A symmetric, there are two cases consider. Okay. Of course, in the general case, when A is complex value, hat is complex value, things are a bit more difficult. Okay. Eigenvector subspace approach is particularly useful for symmetric. So for symmetric matrices, you can use eigenvector subspace, Krylov subspace method. We are going to discuss in the sequel later on. Okay. So, okay, singular values for a linear map. These are the eigenvalues, lambda. Okay. You see that the space is X, the input and output for the linear map are the same. A singular value is for a linear map from X to Y, okay, with a psi in X and sigma a real number, you can write this problem B star B. Psi is sigma squared psi. This is the singular value problem associated with the linear map Bx. Okay. Note that in the case of the singular value, where if in the eigenvalue decomposition the spaces should be the same. Okay. In the singular value decomposition, B can be from X to Y and Y can be different from X. Okay. And this is interesting. Now you have singular value decomposition. This is the original. And then you do note that you have orthogonal transformations here, U and V transpose. And the approximation is to neglect this part and take it 0. Okay, and then you get B hat, a singular value based approximation of the original linear map B. Note that in this case we can have an error bound if we didn't have something for the if there wasn't much based on the eigenvalue decomposition. Now in the case of the singular value decomposition, we can evaluate the norm of the error between the original and the approximation using the left out or the neglected singular values. Okay, so singular value decomposition is appropriate for approximating an input-output map, and not necessarily the eigenvalue decompositions. That's why balanced truncation is much more important and better than model approximation, okay, than the simple eigenvalue decomposition. Okay. Now, there is here a revisit of the Gramians, and I think this is a very nice slide to help you recall the notions of energy functions as well as Gramians. We have the original system here. We have the two controllability. So this is controllability Gramian, and this is the observability Gramian. Okay. They call it here P and Q. And we know that they are related to the energy functions. The controllability energy function, which is the minimum effort to control a state from 0 to minus infinity, or to bring the system from 0 at minus infinity to psi at 0, is given by this function, which depends on the inverse of the controllability Gramian. On the other hand, the output energy, the future output, this is the past input energy, and this is the future output energy. Okay, so we have these two quantities. Okay, and we have this. This is given by this. They said prove the Lyapunov equation for Q. We just accidentally, without knowing what's going on, we have just done this. Where did we do that? We did it here. Okay, we just did it here. Okay, we proved that that LO, okay, is a Lyapunov function. Is a Lyapunov function for the given, for the original system. Okay. All right. A balanced realization means that we need to bring P and Q in such a form that they are equal and diagonal, and we call it sigma. And the diagonal contains the Hankel singular values of the system. If the Hankel singular value is positive, then that state is controllable to a certain extent and observable to a certain extent. If the Hankel singular value is 0, then it's not controllable, is neither controllable nor observable nor both. Okay. Hence, in balanced coordinates, the energy functions, the controllability function and the observability function, have specific measures where you can essentially, okay, so this is sum of half xi squared 1 over sigma I. I from 1 to n. And this is sigma I from 1 to n half xi squared sigma I. Okay? So I just remind you, sigma small, effort big, and output visualize not too much. Sigma small, sigma large, control effort small, observation large. And that's good. Okay? Basic contribution is to diagonalize two matrices corresponding to two positive energy functions simultaneously. Okay. Equivalent problem. And now we go. They present here the relation. They present here the relation to the model problem. Okay. Mode decomposition is to diagonalize two symmetric matrices M and K simultaneously. Okay, corresponding to two semi-positive definite energy functions. So here you have the kinetic. This is the kinetic energy. Okay, Q is displacement. Q dot is velocity. Okay, so this is kinetic energy and this is potential energy. Okay, kinetic energy. This is given by damping. Actually, it's given by the speed, no, not by the damping. This is given by the velocity. Okay, velocity of motion, and this is given by the displacement of motion. I mean the position of the body while it's moving. It doesn't matter here that it's rotation or translation. For rotation, you have torques. Here we've got forces. This is usually given by elastic force, okay, or elastic effort, or gravitational effort. Gravitational effort. Okay, so these are things from mechanics, which are important. So this is the kinetic energy, and this is the potential energy, not potential without hyphen. Potential. Okay. The corresponding eigenvectors qi tilde, they are the natural modes of vibration, of movement. Okay, of movement. All right. So mode decomposition is diagonalizing. Okay, the corresponding. Can you diagonalize both M and K at the same time is the question, because we can do this in balanced truncation. We can do this with a balancing transformation. Can you do this for this particular mechanical system? Okay. Moreover, can you diagonalize simultaneously if you have the complete physical system? Because here you have no elastic force. Okay, but here you have elastic force or gravitational, okay, which depends on the position. Can you diagonalize this simultaneously? I think here is a mistake. Mind you, this is not, this is just Q. This is not Q dot. It's a mistake here. This is just Q. Okay, because otherwise it doesn't make sense. You have only damping and no potential term, and that's ridiculous. You see my point, don't you? Okay. This is I don't know why this is Q dot either. Should be EMQ. Okay, these are mistakes. Okay. This is again, it's the same. Okay. Now this is a general. Now you're adding damping. This is damping. Okay. Now you're adding damping. Can you do this? Can you diagonalize them simultaneously? Because you can take the two functions, observability and controllability function, and you apply a coordinate transformation. Okay. And then you get the new Gramians, and you select a specific t such that, so t is what, such that p tilde equals q tilde equals the diagonal matrix like this. Okay. And here it shows you, you just recall here how to get the balancing transformation, which is this one, based on the Koleski factorization of some Koleski factorization of the Gramians. Okay. And it shows you here how if you apply this coordinate transformation, then indeed p tilde and q tilde, they're both identical and equal to sigma, a Lyapunov function. Okay, can you find a Lyapunov function, is the question, using these? Of course you can. Of course you can. And you do this Lyapunov balancing based on P and Q, and the balanced Gramians. The balanced Gramians give you all these equations. Okay, all these equations. Mind you that sigma 1 and sigma 2 are diagonal matrices. Okay. And then you do balance truncation in the sense that you only keep the first part. But now you can actually split the entire system into two subsystems, subsystem 1 and subsystem 2. They're all stable because of the Lyapunov equation, and the stability is preserved because, again, the Lyapunov function property of the observability function is preserved, okay, through balancing. All right. And you get the Lyapunov equations for the subsystems. Okay. You get the Lyapunov for the subsystems. Here they also show you the Riccati equation of the inverse of the controllability Gramian, stemming from the optimization problem of getting the minimum input effort to steer the state from -infinity to 0. Okay. All right. Hankel singular values, we recall, these are given by, through balancing, they can be easily obtained, okay? And then you get this wonderful property that you have an error bound on the infinity norm of the error given by twice the sum of the truncated Hankel singular values, okay? L2 gain and H infinity norm. There is a discussion here. It gives you the definition of the H infinity norm, the definition of the L2 gain. Okay. For linear systems, due to Parseval, to the theorem of Parseval, these are equivalent notions. Okay. Of course, you can talk about storage functions for nonlinear systems and so on and so forth. Lyapunov, not Lyapunov. Lyapunov function. You can do this for dissipativity as well, and so on and so forth. Okay. Now, if you do reduction by one dimension, the Gramians have this form. Okay. And the objective to prove is this one. All right. And it gives here a dissipativity type of proof for the error bound on the approximation error. We are not going to get into the details of this proof. This is different from the book of Antulas, where you had a completely different proof. This is a dissipativity perspective proof. Okay, this is a physical system, nonlinear system perspective proof using storage functions. Okay, using storage functions. I'm not going to get into this. Okay, the scalar sigma i's are called Hankel singular values because they are the singular values of the Hankel operator, and we have discussed this so far. It shows you here what the Hankel operator is. Here you have controllability operator, observability operator. Look at the controllability operator. Essentially, you take an input backwards in time and you apply it to the system, and you check the state x0. Then you do not consider an output here. The observability operator, you turn off the input at moment 0. You have the initial condition x0, and you look at the output free evolution of the system. And this is the controllability operator, observability operator, sorry, and this is the Hermitian of the controllability operator, okay? And you note that the Hankel operator is observability operator of controllability operator. Why? Because the controllability operator takes you from input to the state, and the state to output, you got the observability operator. Okay, so y is O of x, x is C of u, so y is O C U. Okay, well, here he was, it was much easier to write. This was lazy. It was easier to write the Hermitian, the adjoint operator of the controllability operator, rather than write because this is minus infinity to 0. E to the power AT U B U, something like that. Okay. So the Hankel operator is an operator that maps past input to future outputs. Okay. Past inputs, future outputs. Okay. Now this is the Hankel operator. Okay. This is the usual input, and this is the usual output. Okay. This is the system. Okay, this is the system, the usual, the natural flow of time. Okay, this is the whole evolution, and when you do truncation, you just match this part of the output. Hankel singular values. So these operators are related to the Gramians, of course. Q is O adjoint times O, and P is C times C adjoint, and the singular values are H adjoint H. V is sigma squared V. Sigma squared V is H adjoint H. It's OC star OC. Okay, this is H star. And this is H star. And this is H. O star OC star OC. That's C. So when you do adjoint, okay, so OC star is C star O star OC V. Okay, O star O is Q, the observability Gramian. So essentially, the Hankel singular value relationship is C star Q C V. This is the problem of determining the Hankel singular values, the singular values of the Hankel operator. Okay. Okay. And also keep in mind that you have C star equals okay, so now you take P. No, you don't take P. You take C of this. You apply the operator C to this, and you get what? You get sigma squared CV, because sigma is a scalar, so goes out. Okay, so you get C sigma squared V equals C star Q C V. But this is P. You get PQ. Okay, and sigma squared commutes with C. Why? Because C is a linear operator, by the way, and sigma is a scalar, so it goes out. So you can easily write the Hankel singular value problem in this form. So this is an eigenvalue problem. It's an eigenvalue problem. So you can see here that indeed the Hankel singular value problem is an eigenvalue problem of the matrix PQ. Okay. So the Hankel singular values sigma i's coincide indeed with the singular values of the Hankel operator. What's the meaning of the singular value eigenvector? Okay. We have here the Hankel norm, so it's probably it has something to do with the Hankel norm, okay, which is this evaluation of the energies, okay. It's the supremum of the quotient of the Hankel applied of the output, future output energy with respect to the past input effort. By definition, we have this relation. We saw this before. We've seen this before, okay. Optimal Hankel norm approximation, okay, you have to minimize this norm, okay, and we have a theorem by those two, by three people, Adamian, Aaron, and Krein, telling us that the k+1 Hankel singular value is the infimum of this Hankel norm. Okay, of course here they are recalling the Hankel norm, optimal Hankel norm approximation, which we discussed at a certain point, and you can all read about it once again. Okay. All right. This is a very interesting table because you get the upper error bounds. Okay, so in balanced truncation, the only upper error bound is this one, whereas in Hankel norm approximation, the Hankel norm is upper bounded by sigma k+1, whereas the infinity norm is upper bounded by the same, twice the sum of the truncated Hankel singular values. Note that both in balanced truncation and Hankel norm approximation, the error bounds for the infinity norm are identical, are totally identical, absolutely identical. So why put so much effort? So they're essentially pretty much solving the same problem, even if they are not explicitly showing that or exhibiting that. Okay. Now we have variations of the balanced truncation. You can preserve structure. You can preserve. We know that stability is preserved, so you can preserve structure. You can preserve all sorts of interesting properties. Okay. Now we had as energy functions, we had the controllability and the observability energy function, but they are not the only possible energy functions we can think of. We can have other types, depending on properties of the systems, we can have other types of energy functions to be used for balanced truncation. Okay. Minimizing the approximation is considered only approximately okay. Variations of the balance realization. Instead of conventional balancing, any pair of Lyapunov, these are Lyapunov functions essentially, of the form x transpose P inverse x and W and x transpose QX can be used for balancing. Indeed, if you can cook up or come up with any type of energy function of this form, we are talking linear systems, so we are talking about quadratic functions, and energy is quadratic. Energy is always positive. You do not need to listen to the stupid people on the TV telling you about negative energy. There is no such thing as negative energy on this planet, so far, to the best of my knowledge. Okay, there is no such thing as negative energy. Only stupid, uneducated people, illiterate people, which is the majority. Well, anyway, at least in this land, on this land, they tell you on TV, laughing their mouths off. They're talking to you about, or they're telling you, they're showing you, or okay, negative energy. There is no such thing as a negative energy. I am feeling a negative energy. This is ridiculous. Okay, you cannot feel negative energy because the energy is positive whatsoever. Otherwise, it is not an energy. And it's not me who tells that, it's the physics who tells you that. Okay, the physics of things. There is no such thing as okay, there's negative power. That's completely different in electricity. And not only. And in thermodynamics, you can have negative power because the power is, in some sense, the derivative of the energy. Okay, that can be negative, and we notice that because we like to have negative evolution, time evolution of the energy along some trajectories to be able to infer stability from that. However, there is no such thing as negative energy. You can have negative power, okay? This is just science philosophical discussion so we can know where we are. Okay. Fine. So you can pick any two Lyapunov functions, quadratic Lyapunov functions, and you can try to balance them. Okay. We can have Riccati equations. Okay. The conventional case is this one. And if you take this general Riccati equation and you set up these quantities to be different from these values, you can easily come up with new energy functions. Hence, you can get bounded real balancing where you get two Gramians of this form. This is a Riccati equation. These are both Riccati equations. You can have the positive real balancing with these types of Riccati equations. And here, please note that you have to have this condition that d plus d transposed, where d is the fit-through term, needs to be non-zero. Okay, so you can, it needs to be invertible. Here it's much easier. Here, if d is 0, things are much easier if d is 0. But here d cannot be 0. D cannot be 0, and that's a big problem because even passive systems, they need not have a feed-through term. However, there is discussion about singular optimal control, which is a completely different discussion. And we can have stochastic balancing where we pick other types of quantities. So we can have variations, okay? Here it's explained what bounded real is, okay? And that you can have extremal solutions. You can have, so essentially, the Gramians sit in between a minimum and a maximum in both cases, positive real and bounded real, okay? Note that Z max is Y min, and Z min is Y max. There is a relation between them, okay? And bounded real balancing means that you bring the minimum, okay, the extremal solution, you bring them into this form, okay? You can also get an error bound for this. You can get an error bound for this, okay? It's a strange error bound, but it is. Okay, using spectral factors. Okay, positive real balancing is the same story. You have two Gramians from the required supply and the available storage, and these lie between minimum and maximum solutions, where you can have, and essentially you need to balance two of the extremal solutions to be equal and diagonal. These are called positive real Hankel singular values. And you can get an error bound. Which is a bit more strange. This is, if you look at it, it looks like a frequency-weighted error bound. Notice that, again, this term comes into place. So we have an issue about that. Okay, so it can be regarded, it says here, as frequency-weighted model reduction with the input weight and this input weight and this output weight. It's very interesting, huh? Stochastic balancing again. Okay, let's skip a bit through this. And there is one notion we haven't discussed so far, we can also encounter a so-called cross-Gramian, but this cross-Gramian is rather strange. Okay, it's rather strange. It's the solution of some mixed Sylvester equations. So if you notice, the cross-Gramian gives you simultaneous information on input and output. Simultaneous information. So this is like a mixed Gramian giving you information about the input-output mapping in one shot, in one quantity. It satisfies this general Sylvester equation. And if the system is symmetric, that means a system is symmetric. This is equivalent to saying that H of S equals that the transfer matrix is a symmetric matrix. That's what a symmetric system is. Physically, it is related to the nonlinear notion of a gradient system. Okay, I'm not going to get into these details. Okay. The cross-Gramian, notice that the cross-Gramian is much easier to compute because you only need one Gramian. So in the case of symmetric, for instance, can you give me an example of a class of systems always satisfying this property? So H is a matrix, okay? HS is a matrix with P inputs and P outputs and M inputs. Can you give me a class of HS that always satisfies this property HS equals H transpose S, please? I hope you're here next to the computer so you can hear me. You can hear my question.
Yeah, we can hear you.
Okay, fine. So think of a class of systems where this is always the case. H equals H transposed, always. It's under your nose. You just need to think a little bit. Which class of systems always satisfies HS equals H transposed S? Look at the size P times M. Can you give, is there a case for specific values of P and M where the property H equals H transpose is always true?
Single input, single output systems.
Exactly. Very good. This means that for P equal M equal 1, H of S transpose of S. Okay? CISO, true. Very good. So for the CISO case, you can always do this. Compute only the cross-Gramian. It's enough. You do not need to perform for a single input, single output system. You do not need to perform balanced truncation in the sense of 2 Gramians. That's too much. Okay? It's enough to have only 1 Gramian. And please note that in the symmetric case, we have this very important relation, the product of Gramian, of controllability and observability Gramians PQ is the square of the matrix S. Okay, you can prove the Sylvester equation. That's not difficult using the definition of X. And you can also prove this relation in the symmetric case. It's not difficult. Okay. You can also generalize this. Actually, this can be generalized There are papers, if you look it up on the internet, generalized to generalized to non-symmetric case. Non-symmetric case. It can be generalized to the non-symmetric case. The cross-Gramian balancing. Then we have frequency weighting, okay, where you add weights to the input and the output of the system, input weights and output weights, where you have the input and output weighted, input weighted Gramian and output weighted Gramian. Okay, you can have this for a finite domain. You have all the discussion about frequency weighting. We discussed it so far, and these are the Lyapunov equations for these two particular Gramians. And you get the state space model for the input or the output weighted system, and you get the weighted Gramians, and you take only this part and you balance it, and then you perform truncation and you get an error bound. The thing is, if you remember, I was telling you that one side weighted case, okay, we have the stability guaranteed. We have the stability guaranteed. Otherwise, it's not true. It's not true. Okay. So for one case, it's good, but this is not 0. I think he wanted to say 1. You cannot take it 0. Okay. Stability is guaranteed if you have either only input or only output weighting. If you take both simultaneously, there is no stability guarantee whatsoever. Okay. And here it shows you how you perform the frequency weighted balance truncation. And I remind you that this is related to the closed loop balance truncation based model order reduction. You also have a self-weighted method where you pick the input weighting to be the identity and the output weighting to be the inverse of the original system. Okay. You can also do balance truncation for the unstable system, where you have time-limited Gramians. These time-limited Gramians, they also satisfy some strange Lyapunov equations, and then you get a reduced model. You can do coprime factorizations, and these coprime factorizations are related to closed loop and to the last subject and the interest at this point, model order reduction of the controllers. So you convert the unstable system into stable coprime factorization, and then you can apply balance truncation. And you also can get an error bound for this. Okay, so you want to balance the balancing of coprime factor representation. Essentially, you think that you have a linear quadratic regulator. So you get this control law over the input, where X is the solution of this Riccati equations. You have been studying LQR, those of you who attended B1 last year. In the last semester, this time last year, you had a lecture on optimal control, didn't you? And you studied this LQ, linear quadratic regulator, at that class. So the map from the new input V, okay, to the graph defines a coprime image representation of the system in this form. This is the coprime representation. Notice that the use of the linear quadratic regulator gives you the stable, a stable system. Okay. When this is normalized, the L2 gain of this is 1. Okay. And then you can do balance truncation. You do balance truncation. Okay. IG. IG is this one. Okay. So observability Gramian of IG is Q, and Q is equal to X. Okay. So balance truncation is again a coprime image representation of the reduced order system. Closed loop Gramians. Okay. So this is where we get to the moment of the controller model order reduction. For a closed loop system, so if you, this is the plant, GC is the controller, you have the error, you have the reference, you have this is the control. Okay, this is the control, right? Okay. For a closed loop system with a plant G and a controller GC, we consider a problem to reduce the order of the controller G. C. This is the main purpose. This is the main purpose of controller reduction. Okay. If we want to maintain the effect of the controller GC with respect to the reference input R, so if we want to preserve the map from R to U, okay, you want to preserve the map from the reference to the control. Okay. Then you apply frequency weighted model reduction, where you use this input weight. You use this input weight. Okay. If we want to preserve the map from R to Y, so if we want to preserve this closed loop map, okay, then you do again input and output. So in this case, if you want to preserve the map to the controller, you only need input weighting. But if you want to preserve the input output, then you need to use input and output weighting of this form. You can do it. You can do model reduction. You reduce the controller. However, the stability of the closed loop system is not preserved this time. It's not preserved this time. You see? This is bad. Okay. Now you can do, in general, you can look at interconnected systems, and you can do generalized Gramians defined by linear matrix inequalities, this time by Lyapunov inequalities. Okay. And you have this interesting result. Suppose that there exist generalized Gramians in this form. Okay. Divided according, these are subsystems, so this is defined according to the subsystems, to the structure or to the graph, okay, of the system. Then balanced truncation for each subsystem preserves the stability of the whole feedback system. This is a very strong result, okay. So reducing each of these quantities preserves the stability of the entire feedback system. Okay. Of course, we imply that each subsystem is asymptotically stable if we want to have that. We also have subspace balancing, and again, this is related to closed loop balancing. Okay. We can have subspace controllability and observability Gramians, P sub and Q sub. They are similar to frequency weighted balanced truncation. Okay. Subspace balancing, we get the so-called partial singular values. You do linear fractional transformation type of transformation, an LFT on this system, okay? Because you want to reduce this part, okay? You want to reduce this part, so you need to use this transformation to emphasize only the coordinates of the controller, because that's what you want to approximate. Okay, that's what you want to approximate. Okay, and then you have balanced truncation of the some M and N matrices. I don't know where they come from, and alpha. Okay, where M equals N times this strange alpha, okay? And you preserve a strange sort of Lyapunov equation. So you can do, once you apply this LFT, you can do, again, balanced truncation, okay? You can do, again, balanced truncation, and you can do model reduction completely. You can apply this to controller reduction. You can apply this to controller reduction. Okay, controller containing also an observer and all of these things. Okay, and it shows you here how to apply this. It shows you here how to apply this. Okay, so this can also be applied to. This was the main goal. That's why I was doing all this recap and this new perspective on valence truncation, so we can easily understand the notion of controller reduction and how this is built. Okay. Okay. All right. That's pretty much it at this point. If you have any questions, please. Have you got any questions, please? Hmm? Any questions, please? I'm waiting. All right, fine. Let's have a break and then let's. Okay. Then let's proceed to the last part of this class. Okay, moment matching based model reduction. Okay.
Okay.
Okay. Okay. I'll see you in a few minutes.
Mhm.
Okay. Right. I'm back, please. Okay, let's just go.
I'm here too.
Okay. So the last part of our lecture of this class is another set of methods, the so-called Krylov-based approximation methods. Okay, what's the idea? Okay, so let's go back and look at the model order reduction problem. Okay, so we start with a system, okay, with inputs and outputs and the state, okay, x, u, y. X is of dimension n, y and u can be of several dimensions, multiple input, multiple output, single input, single output, and so on and so forth. And you want to approximate this with another type of system, x hat, which is ax hat plus bu. U is identical, but then you get a new output y hat, cx hat with x hat, or maybe I should use my notation, my preferred notation. I don't like this one. I'm using the notation in the variable. I'm using the notation in the variable psi. Okay, psi dot is x psi plus gu, and eta, let's call it like this, is h psi. With psi in R ni smaller than n. And you want something from these two. If balanced truncation was looking at these things from this perspective of balancing and truncating the Hankel singular values, okay, and finally having, so BT, okay, Hankel singular values sigma of A, B, C, sigma from sigma I from with I from 1 to ni, they were identical to the Hankel singular values sigma I, okay, of f, g, h. This is imbalanced truncation. Now we have a different approach. Both of these functions have transfer function. We have hs or ks. Let's use k. Okay. We have ks, which is c si minus a inverse b, and we have kgs. Let's call it like this: h si minus f inverse g. Okay. Note that both transfer functions have the same dimension. Okay, so both k and kg belong to the same, because we have the same number of inputs and outputs. We do not touch that. That's untouchable. Okay. However, notice that the dimension, okay, this is ni. Okay, so this is a transfer function of dimension ni. This is a transfer matrix of dimension n, system dimension. Okay. Now, what should be the criterion for this? Notice that, for instance, this function, okay, admits around any point S0, okay, let S0 be a complex number less than the poles of the transfer function, okay? I remind you that Ks is 1 over det Si minus A, and here you can call this Rs, okay? So the sigma A, okay, is the poles. Okay, we assume it's minimal and all this and all that. Okay, the sigma A are the poles of Ks. They're the poles of Ks. So S0 should not be a pole of Ks. Now, apart from the poles, these discontinuities, Ks is what's called in complex analysis analytic in the complex plane C, with the exception of the poles, which are a limited number of singularities. Consider any point, complex point, which is not a discontinuity of Ks, then you can write Ks as a Taylor series, or well, Laurent series, but here we restrict ourselves to Taylor series expansion, Ks0 plus K prime S0 times S minus S0 plus K second S0 S minus S0 squared plus, this is, I think, 1 over 2, plus 1 over 6 K3 times S0 S minus S0 to the power 3, and so on and so forth. Okay? Where's my friend? Andrei, it was your question. Look, isn't this related to lab 5?
It is.
Oh, you see now? You see? These coefficients. Okay? Similarly, Kg, okay? Kg S is Kg S0 plus K prime G S0 S minus S0 plus half Kg second in S0 times S minus S0, S minus S0 to the square plus 1 over 6 K3 times S0 SG minus S0 to the power 3, and so on and so forth. You see? They both have a similar Taylor series expansion, okay? Now, what do you think would be the criterion of the model reduction? Assume, so Ks is dimension n, okay? And Kg is dimension ni. So what do you think would be a natural criterion to determine the dimension ni of the reduced function, looking at the Taylor series expansions? What do you think is going to be the model reduction constraint criterion this time? Hmm? Okay, do you have an idea? You cannot ask KGS to be equal to KS to be equal to KGS for all S. You cannot do that, can you?
No, because
No.
they have different dimensions.
Okay, yeah, sure. No, but you okay? So of course they have different. No, but they have different. You can ask them to be equal, but they have different dimensions in the system. Okay, you can still ask that because they are both P times M matrices. So you can ask them to be equal, but that's not natural. But what is a natural thing? You truncate the series, both series at ni, truncate at ni, okay? And then impose K, D, let's say DI, KS, DSI, evaluated in S0, these are differentials, okay? B, DI, KGS to DSI in S0, I from which value? From where to where? Actually, you need to truncate at n minus 1. From I, from which value to which value?
From 0 to mu minus
To
1.
n minus 1, exactly. So this is the moment matching problem, general problem. Okay? Given two transfer functions, transfer matrices Ks and Kgs, okay? No, given to one transfer, given Ks, find Kgs of dimension n, okay, such that these conditions are satisfied simultaneously. This is called moment matching. Moment matching. Of course, there is a big mathematical background behind all this. The general problem, this comes from the general problem of interpolation. Okay? So essentially, given two sets of data, U, this is U1, U ni, and this is Y equal Y1, Y ni. Okay? Find F defined on U with values on Y, where these U and Y lie, such that F UI equals YI. This is the general interpolation, mathematical problem of interpolation. Okay? Now, based on this type of thinking and coming with ideas from linear algebra and from solving linear systems, people came up with this specific methods which form a big group of very efficient model order reduction methods, which we are going to discuss now. It all starts from ideas such as eigenvalue computation. Okay. And they say here that the two-norm approach to system approximation requires dense computation. Okay. So you realize you need to compute stuff about the two-norm minimization. We talked about minimizing the infinity norm or the Hankel norm. Now we are talking about minimizing the two-norm approximation. So essentially, you would like to solve min by all kg, k minus kg2. This is the two-norm. Now, this is a bad problem. This is a bad problem. It's nonlinear from an optimization point of view. It's infinite dimensional. And especially, and the worst part, it's non-convex. It's non-convex. This is the worst part. So it's a bad optimization problem. Yeah. It's a bad optimization problem. Okay. So we have to do something about it. Okay. So solving this problem, okay, requires dense computation of order n to the power 3. In general, this is bad. And storage of n squared. So you need a lot of storage and you need a lot of computational effort. Okay, where n is the dimension of the original system. Consequently, it can be used for a system of moderate complexity only. Okay, and balanced truncation, for instance, is used only for moderate dimensions. Okay. Now, people came up with lots of iterative algorithms called Krylov-based algorithms, which are an alternative to the balanced truncation we have been discussing so far. Okay. And here they present a basic so-called Krylov iteration. Given an n by n matrix and a vector b, okay, we consider the vector v1b over normalized is the normalized version of the vector b. At step k, we have the iteration that avk is vkhk plus fk e star k. E star ek is the vector with the dimension with elements 0 and only one element on the position k being 1. Okay, it says here ek is the k's canonical vector, v is the column vectors. Okay, v star k vk is the identity. Okay, and a is projected onto the subspace spanned to the columns vk. Okay, so a takes this final form. The computation complexity required for k steps in this iteration is O n squared k, so this is not n to the power 3. And storage is linear, is nk. Okay, this iteration is applied to sparse matrix A, in which case the complexity reduces further. Okay, so this is all about, it all comes from computing matrices and eigenvalues for matrices. That's where it all comes from. Okay, the iteration has rich structure, it says here, involving subspace is spanned by the sequence of vector b, a, b, a square, b, ak minus 1, b, called Krylov subspaces. This is from the book of Antulas. You can always check the book. Okay. All right. Uses of the Krylov iteration. Okay, so this is the general Krylov iteration. That's what it says here. And where is it used? You see here that you project the matrix onto some subspace, or you reconstruct the matrix from this H matrix, adding, if you can see here, adding a rank 1 update every time. This is a rank 1 matrix. Fk is a column, Ek star is a line. So a column times a line makes a rank 1 matrix. Okay, as we all know. Where do we use this specific Krylov iteration? Okay, and here they are very nicely represented or exhibited, the three main uses of such an algorithm. For instance, the iterative solution of the general algebraic system AX equals B. In this case, we seek to approximate the solution X, it says here, in an iterative fashion. Okay, Krylov methods are based on the fact that successive approximants belong to the subspace Ki mentioned above, the Krylov subspaces. Okay, and you have two algorithms that compute such a Krylov iteration. Okay, Arnoldi and one-sided Lanczos algorithm. Okay, that construct orthonormal basis for these subspaces. Then, to compute the eigenvalues of A, it says here iterative approximation of the eigenvalues of A. Okay, so B is not fixed in this case, and it shows you here all sorts of versions of the use of the Krylov step for the eigenvalue problem. Okay, and finally, the last one is the approximations of linear systems through moment matching, which is in the chapter 11 of the book. Okay, this is from the Antulas book. So now they present the iterative and the nice features of the numerical algorithms, and then it's applied algebraically, so to speak, to linear systems. Finally, we are going to come up with a new modern vision of moment matching problem from a system theoretic perspective, using specific notions that you have been studying throughout your bachelor studies, and we have been recalling, or we were recalling earlier in this lecture, such as steady state response, stability, and all these main notions and ingredients related to systems theory. Our approach is much nicer than this algebraic approach in the book of Antulas, because we can present families of reduced order models, and we emphasized the presence of specific degrees of freedom in this class of models, which are not present or are difficult to understand in this algebraic form. The algebraic form is very restrictive. You can only compute one model. Actually, your one model is part of a family of models. So our approach, which you're going to see probably next time or at the end of this lecture, is the so-called time domain approach taken to moment matching, which I think is much easier than the whole thing we present in this part. Okay, that's the easiest to understand for a control engineer from my point of view. Okay. Okay, so let's see what's in the introduction of this chapter. Okay. So this is a chapter about eigenvalue computation, which is quite relevant. Let's see. Okay, so this is a recollection of the definition of an eigenvalue, and its corresponding eigenvector. And the lambda and x is called the eigenpair of the matrix A. Okay, the problem is nonlinear in lambda. Okay, and in the entries of x. Nonetheless, it can be solved in 2 steps as follows, it says here. First, you note that for a fixed eigenvalue, a minus lambda I has a non-trivial null space or kernel, okay, of course. And since we are in a finite dimensional space, such as Rn, this is equivalent to the determinant of the matrix A minus lambda I being 0, okay? So you can see here the polynomial chi A of psi is the determinant of psi I minus A, which can be written as the product of the monomials created using the eigenvalues, okay? This is the characteristic polynomial of A. Then lambda is an eigenvalue if and only if lambda is the root of the characteristic polynomial. We know that. This is just a recollection. Consequently, the eigenvector is a member of the kernel of the matrix A minus lambda I. Okay? All right, and here there is the definition of algebraic and geometric multiplicity of an eigenvalue. Okay, and we know that if the eigenvalues are distinct, then we can have a diagonal matrix. If they are equal, we can have a Jordan block based on the Jordan canonical form. Okay. All right. And then there is also the notion of similarity between 2 matrices. We know that already. We're very familiar with that. We've been using it throughout the time a lot, especially in balanced truncation. A subspace V including X is A invariant if A times V, if multiplying to the left with the matrix A all the elements in the space V, it's again included in the space V. Okay, let the columns of V in R and K form a basis of calligraphic V. Then there exists a matrix such that this thing happens with the spectrum of the matrix H included in the spectrum of the matrix A. So the eigenvalues of H are a subset of the eigenvalues of A. Okay, so the goal in this section is to discuss methods for obtaining approximate invariant subspaces, say V calligraphic, where the residual is orthogonal to some k-dimensional subspace W, which is spanned by the columns of W. You see R is orthogonal to W. That means that W transpose R is 0. And AV is VH plus an update R. This looks, again, like the Krylov iteration. Okay? The orthogonality property is also known as the Petrov-Galerkin condition. And that's why these projections, because as you'll see them here, these projections here, which compute A, H is the projection of A onto the new subspace. This is called a Petrov-Galerkin projection. This is a biorthogonal projection, and the approximate eigenvalues are the eigenvalues of H. Okay, these are approximate eigenvalues of A. Look here. A is of dimension n, and H is of dimension k, or ni. Okay, In many times in the Arnoldi process, especially, the people take the subspace calligraphic W and V to be identical, and then the H matrix is easily computed as V star AV. Okay, here you have about condition numbers. These are details which I'm not going to get into. All right, and shows you how to compute pseudo spectra. Okay. This is also used quite a lot in image processing, this type of things, because the images are huge matrices of data. Okay, and here they present us iterative methods for eigenvalue estimation. Okay, we have the sure triangular form. Every square matrix is unitary, equivalent to a triangular matrix. So A is QT, Q star, where Q is orthonormal and T is upper triangular, and Q star is the identity. Okay, and you can see here perturbation of the eigenvalues of a 12 by 12 Jordan block and its pseudo spectra for real perturbation. This is a funny picture. Anyway, we have a theorem for Hermitian matrices. If you have a Hermitian matrix A equals A star, Hermitian means so A star is A conjugated and transposed. Yeah, if we talk about if A is a real matrix, then it's just the transposition. But this is a general case of complex matrices. So given a square matrix of dimension n, which is Hermitian, there exists a unitary orthogonal coordinate transformation such that, so you can split, you can compute, you can, in real numbers lambda I, such that A is U lambda U star, and can be written in this form, where you are the right and left eigenvectors of A and form an orthonormal basis for Rn or Cn. Okay, so you can always write a Hermitian matrix in this fashion, and then you remember the QR factorization given a matrix A in R and which is not square, square, of course. There exists a matrix Q whose columns are orthonormal, so Q star Q is the identity, and upper triangular matrix R such that A is QR. Okay, A is QR, so you can always factorize a non-square matrix A in this form. We have a definition called the Rayleigh quotient of a square symmetric matrix. Okay, so we have a measure for the matrix in terms of the factorizations. Okay, we have a procedure here, the Rayleigh-Ritz procedure. So given a Hermitian matrix, the columns of V, and consider the columns consider the matrix V with orthonormal columns. That means that V star V is the identity. We consider the eigenvalue problem projected onto the subspace spanned by the columns of V. So X is Vy. Now, AX is mu X plus W, where W is orthogonal to V. Okay, and here you get finally that V star AVY is mu Y. So this is an eigenvalue problem. This is an eigenvalue problem for this matrix. Now, so the matrix A hat, V star AV, is a symmetric matrix. Okay, and let its eigenvalues be mu1 up to mu r. Okay, by some theorem, you have the mu I lie in between lambda I and lambda n minus r plus I. Okay, so mu is an approximation of the real eigenvalues lying in this region, Lambda hat, if you have the eigenpair of the A hat, which is V star AV, is an eigenpair of lambda hat. Then lambda hat is called the Ritz value, and Vx hat is a Ritz vector of the matrix A. So besides eigenvalues, we have these Ritz quantities that characterize an eigenvalue projected onto a subspace like this. Okay, and look here, given any alpha and v with v of dimension with norm 1, consider the quantity beta being AV minus alpha v. Then A has an eigenvalue in the interval alpha minus beta, alpha plus beta. Okay? And the interval is minimized if alpha is the Rayleigh quotient of B. So this result essentially is telling you that you can approximate the eigenvalue in a specific interval with this type of projection algorithm. Okay? Okay, you also have other methods presented here. Okay, all sorts of methods, subspace iteration, all sorts of things. Very interesting, which I invite you to read and to study later. Okay. In the iteration methods described above, a sequence of vectors vk is constructed that converges under mild assumptions, such that it converges under mild assumptions to the eigenvector corresponding to the largest in absolute value eigenvalue. So this method above allows you to start and compute an approximation from the largest eigenvalue onwards, okay, or backwards. The convergence rate can be slow. However, notice that each step only the last vector of the sequence vk is used. The approach described in this section attempts to keep the information. Okay. All right. So we want to approximate the eigenvalues. Okay. The approximate eigenvalues are eigenvalue of the projected matrix A given by 10.4. Let's go back to the relation 10.4. No, who finds it? Oh, by this relation, okay? By this relation. Okay, so notice that you can use this relation to compute, again, to approximate eigenvalues, okay? So our goal is to determine approximate invariant subspaces that satisfy a specific property, and the approximate eigenvalues are the eigenvalues of the projected A. Okay, and we discuss the case, they discuss the case here, W equal to V, but we'll see that in rational approximation we use different. The case, we also use the case W is not V. Okay. Here we have a motivation for Krylov methods presented, and you should look into it because here you start from this specific measure. Okay, it's an energetic measure, just like we discussed before. If you look at it, these are quadratic functions. Okay, so the Rayleigh quotient is an energetic measure. It's somewhat similar to a Hankel singular value. Okay, well, it's not a singular value, but it's similar. The significance is rather similar. Okay. Okay. So an algorithm such as the Lanczos procedure can be derived by imposing the requirement that for that given vi, the next vector in the sequence vj plus 1 is chosen to maximize the eigenvalue like this. Okay, and we only have these quantities and the matrix A. And here it shows you how to compute orthonormal basis to be able to create these very good projections. Okay. All right. Okay. So we have a symmetric matrix A together with a sequence of vector v1 through vk, form an orthonormal basis for the Krylov subspace k index k of A and v1. Okay, so that's something such as v1 a v1 a squared v1 and so on, a to the power k, I think, or k minus 1 v1. Okay, and they use they orthogonalized AVK with respect to all the other VIs, and this is done through a Gram-Schmidt procedure in the new direction in AVK. And here they show you how this is done. They show you how this is done. Okay, and there is the result. There is the result for any choice of, so for any square matrix A. Okay, the coefficients alpha I determined here. There are some look, coefficients alpha I, j equal to 0 for I larger than j plus 1. Furthermore, since A is symmetric, alpha ij is equals to alpha ji, and the coefficients are 0 also for j larger than I plus 1. So this is an approximation, essentially. Now this is an approximation of the original problem. Okay, the above equation can also be written compactly in this form. All right, and it shows you in this specific case you get specific form of the Krylov subspace and of the matrix H. Okay, and then you can get the vectors in the procedure satisfying a specific recursive solution that proves the point of the solution of the eigenvalue of the eigenvalue problem. And then it tells us the convergence of such methods. And then they also explain the Arnoldi method. Okay. Okay. So the procedure from the answers previously applied to symmetric matrices can be generalized to non-symmetric matrices, and the resulting process is called Arnoldi process, depicted in this figure. So you see AV is V times H plus an update R, So the Arnoldi process, given a matrix A, you are required to construct V with the orthonormal columns such that H, this is of dimension K, this H, is upper Hessenberg matrix, okay, and only the last column of the residual R is non-zero, okay. So this is the form of the update we want to construct with respect to matrix A. You see, the H matrix is much simpler, and this takes your mind into the idea of model order reduction. That's why we would like to use these methods, okay, to compute reduced order models, which are much simpler. And this is the upper Hessenberg form of the H matrix, okay. Okay, but this is much more difficult, it says here, than the previous procedure. Okay, and here they present also the properties of such methods, of a method such as the Arnoldi. Okay, which is true in reachable. Okay, the reachability or Krylov matrix. That's R. Okay. And the problem is you would like to derive a process which is iterative, and at the kth step yields this iteration. Okay, these quantities have to satisfy, and there are some conditions. Vk is with orthonormal columns, so Vk star Vk is the identity. The residual Rk is orthogonal to the columns of V. So they satisfied the so-called Galerkin condition, okay? And the columns of the matrix V span the columns of the matrix R, so of the controllability space R, okay? So that's how you build VK as part of this controllability matrix, and you have a nice result here, explaining that this is all very good, okay? We do not look at such proofs, okay? There is also all sorts of forms of these iterative processes. which are presented further on. Okay, and there is an alternative look at the Arnoldi process. Okay, you find an interesting relationship which is true here related to the characteristic polynomial of the matrix A, and you also look at use the QR factorization of the specific matrix controllability matrix Rn, and when you start putting it all together, you get a nice relation of this form where A hat is of this form. Okay, so since you, and then the property of being triangular is kept, and that's very useful. It's also, they also present here properties of the Lanczos method, but the Lanczos method has also a two-sided version, So if the matrix A has to be transformed to three-diagonal form, okay. All right, you see two steps here, and you have this property here. Okay, so this is a better algorithm, and the more we are going to use that in the moment matching, and this gives us more precise approximations than one-sided version. Okay, here you have the algorithms, you have implementations of these algorithms. If you're interested, you can play with them yourselves in MATLAB and compute eigenvalues using this. Okay. There's also other versions with respect to this matrix for these algorithms, which you can look. There's all sorts of versions and improvements. You see, all sorts of versions. And here are some examples. Consider the symmetric matrix A and the starting vector B. And it shows you here the symmetric, Lanczos, and Arnoldi procedures for 1, 2, 3, and 4. Okay, and it shows you how you do all the computations and what the algorithm is producing. Okay, this is very interesting, and I would like you to access and to learn about and study about these things, because they can also be quite useful for you to understand the papers for the exam. The SVD-based approximation methods presented in the preceding 3 chapters require dense computations. That's what we have been discussing. Okay? Their compelling properties notwithstanding, they cannot be applied to large problems. So you see there is a trade-off. SVD-based methods, they are very nice from a theoretical point of view. They are very popular. However, they cannot be applied to large-scale problems. So if you can try yourselves in MATLAB and see how this works. You'll see it requires a lot of computation. You noticed even for the CD player, MATLAB was unable to compute the exact controllability and or observability gradients. It's very difficult, okay, because of this O(n) to the power 3 complexity. Okay, so now the new methods, they are theoretically only algebra. They have no physical meaning. There is no energy functions here. There is no Hankel singular values. It's nothing related to an input-output perspective, apart from the final part when we are going to prove to you that indeed there is a strong connection, and you can start this whole model reduction problem from a completely different perspective than what I'm presenting so far. And these methods with their iterative procedures help us get efficient algorithms completely applicable to extremely large dimensions, such as millions of equations. These are the so-called Krylov methods. Okay. All right. Now, how do we use these methods for model order reduction? Okay. We are going to talk about approximation through moment matching. And here is the definition of the moments. Okay, so a linear, discrete, or continuous time system defined by a convolution or sum of integrals. Okay, so please keep in mind that you have that ys is hs us. You remember this. This is a transfer function, but in the time domain, taking Laplace inverse, it gives you that the time domain response is the convolution between uh, uh, the impulse response of the system and an input. Okay, so it's determined by the impulse. Any linear system is determined by its by its impulse response. Equivalently, the Laplace transform of small h is capital H, called a transfer function. We know that. So this is the class of systems to be studied. Okay. Note that for linear systems in general, and if you look at this, because Hs is Ys over Us, and Y and U are rational themselves, Hs is always a rational function. That's only true for linear finite dimensional systems, keep in mind. There exists infinite dimensional systems, such as the heat equation, look it up on the internet, where this transfer function is no longer rational, it's irrational. Okay, so there exists also irrational transfer function. So in this case, the complexity of the system turns out to be the rank of the Hankel operator H, we have been discussed about so far, or the Macmillan degree of H. Okay, so it's the dimension of the transfer function. Okay, we are talking about minimal systems here, so the Macmillan degree is the same, because we didn't talk too much about Macmillan degree, is identical to the dimension of the denominator of the transfer matrix. Okay, so one way to approximate a system is to approximate its transfer function by a rational function of lower degree. This is what we are going to do next. This can be done by matching some terms of the Laurent series expansion of H at various points in the complex plane, exactly what we discussed earlier. This expansion is for instance, around infinity. You can also have it around infinity, and you can do it in this fashion. Okay, then the HI are called the Markov parameters of the systems. You remember the Markov coefficients or parameters. We discussed about this in the chapter about linear dynamical systems. Then you seek a new function h hat of smaller Macmillan degree or dimension of the system that satisfies, that has this, the identical Laurent series expansion. And if you want these two functions to match, you impose this matching condition. This is called the partial realization problem of a system, and it's also discussed in this book. And we have been discussing the realization problem and talked about the Markov parameters determining uniquely the transfer function and the dynamic of a linear systems in previous chapters. And here they tell us how to apply Lanczos and Arnoldi methods presented in chapter 10 to this, to get the reduced order transfer function. Notice that these transformations, they are applied to the state space realization of the transfer function. Okay, the k-step Arnoldi iteration applied to the pair AB of the system produces a matrix orthonormal columns Vk. A reduced system A hat, B hat, C hat can be constructed applying the Galerkin projection to sigma. So you pick this guy. Okay, I remember that. I told you before, you had an exercise with this. X equals V psi. W transpose V is the identity from the projection. That's because the projection P, which is V W transposed, okay, satisfies the property that P squared, which is V W transposed V W transposed equals, again, this is the identity, equals V W transpose. So P squared is P. So P is the projection indeed. P is a projection indeed. Now you take differentiation with this. This is a constant matrix, and then you get V psi dot is A V psi because it's AX plus BU, and Y is C V psi. But now you want to get rid and you want to have psi dot. So you multiply this by W transpose, and then you get that psi, the reduced order model has psi dot is W transpose A V psi plus W transpose BU. So that's why you get these matrices here. Okay, here W equals V because this is an Arnoldi process. Okay. Now the main property of this sigma hat is that it matches Markov parameters of sigma if you take the expansion at infinity. If you take the expansion at infinity, okay, and you get this relation. These are the Markov parameters. Look it up. We studied Markov parameters a while ago. Okay. Now, this is Arnoldi. If you do Lanczos, you do this one. You do this kind of approach. For Lanczos, you have this general approach. Okay. And again, you can get once again the reduced order model in this fashion. Okay, and it satisfies you see it matches 2k moments here of sigma. Okay, so here you match k infinite k Markov parameters, whereas here you match 2k Markov parameters. Okay, all right. Now here we have a discussion about the moments of a function. Okay, and then we're going to stop. So what are in general, the moments of a function? This is a mathematical notion. So a matrix, if you have a matrix valued function h defined on R to Rpm, the kth moment is defined in the time domain is defined like this. Integral from 0 to infinity tk okay. Now if you take the Laplace transform of this time domain quantity, you get okay, which is this one. Okay, then you get the kth derivative at S0. Then you get exactly the coefficients of the Laurent series of the transfer function. So indeed, moments are identical with the coefficients of the Laurent series expansion of a rational function. For our purposes, we make use of a generalized notion of moments, namely the moments of h around any arbitrary point S0. So this is around, this is to infinity for Markov parameters, and this is, oh no, sorry, this is to 0 here, because you have no exponential, but here you can have the generalized moment at any point at 0, and you get this definition of a moment. You get this definition of a moment. Okay. Now, in the context of the transfer function, because this is much easier to grasp, okay, it's easier to grasp than the time domain notion. Consider h the impulse response of a linear system. Then the impulse response has this form, and this is the transfer function as we know. Okay, then at 0 you get these moments, but in general, for any point S0, you get the moments at S0. So these are moments at 0 at S0, and you can also get the moments at infinity, which are the Markov parameters of the system. So we have three types of modular reduction: moments at 0, moments at any point, and moments at infinity. We'll see that we can do moments at 0 at any finite point, And separately, we can also discuss about, but it's the same thing to do model reduction, doing matching of the Markov parameters. Okay, I'm going to stop here now, and I'm going to ask to ask you for questions. Have you got any questions, please?
So moment matching, it's about Markov matching.
No, 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 no. Markov matching is a particular case at S equal infinity.
Mm-hmm.
You see, you can have moments. You can have moments eta. Let's call it eta at S0. Okay, so S0 can be 0, finite, okay, or infinity.
Okay.
Yep. Yep. Anything else?
You said at the moment that we can apply a method for image. For images, but
No, yeah, no. The notions, the reduction of the eigenvalue computation that you just saw so far, okay, because in chapter 10, the guy discusses about eigenvalue decomposition. That can be used for image processing as well. Yeah, that's used for image processing as well. Those methods for matrices. Okay, because images are matrices of data, right?
Yeah.
Okay, so you can apply, if you want to reduce and you want to have a small an approximation of the image, okay, you want to have the approximation of the image, you can apply those methods, okay.
So
right?
for
Because
compression.
Exactly, resize, compression, you remember convolution, okay? Convolution is also a way to approximate images. But if you look in the book of Antulas, you're going to see a picture and how it's reduced using Krylov iterations. Okay. So model reduction for dynamical systems essentially comes in this algebraic and this numerical efficient methods. It comes from linear systems approximation, solutions and eigenvalue problems and so on and so forth. Okay. Anything else?
From me, not any.
And your friend?
It's fine for me.
Okay. Fine. So please look in the books. Please look in the papers. Please consult all the materials uploaded on Moodle. I think they're quite interesting. And I'll see you next week, where we are going to really dive into this moment matching thing and see the numerical part, and then present a nice system theoretical approach to these methods. Okay?
Okay.
All right. Please tell your and also please do lab 6. Lab 6 and lab 7, look at the date because you need to solve them. Okay? I think the next one due is lab 6. Okay? Please also, there is colleagues who have not done any homework so far. Please tell them that they should do something about it, because otherwise they lose 50% of the points. Okay? Well, never mind. If they are not interested, I'm fine. Okay?
Okay.
Okie dokie. Well, cheers. See you next week.
Okay, goodbye, teacher.
Bye.
See you.
See you
Bye.
next week. Cheers. Bye.